Okay, problem 9.18 introduces the Atkinson cycle, and it gives us this PV diagram right here, and it also gives us the initial temperature and pressure, the compression ratio, and then the heat addition from process 2 to 3 is given to us also. It's 1400 degrees, 1400 kilojoules per kilogram. And the first thing it asks us to do is draw the temperature entropy diagram. So in the problem, it explains to us that process 1 to 2 is isentropic. Process 2 to 3 is constant volume heat additions. So this line from 2 to 3 is a constant volume line. And as you can see, the entropy increases from 2 to 3 due to the heat addition. And then it tells us that process 3 to 4 is isentropic compression expansion, and your entropy decreases with the decreasing pressure. And process 4 to 1 is constant pressure heat rejection. So this line right here is an isobar. Okay, using the information we were given for state 1, all we need is T1 because we're doing an air standard analysis. We will be able to calculate the internal energy enthalpy, the specific volume of the ratio. State 2 will be defined by the specific volume of the ratio, and that's just found using the inverse of our compression ratio times the specific volume ratio at 1. And using this VR2, we can find T2, U2, pressure of the ratio at 2. Now state 3 is defined by the energy balance, and in process 2 to 3 there's no work, there's only heat addition. So we have also neglected kinetic and potential energy. So you will be able to find the internal energy at state 3, this U3 right here, which is equal to the heat addition over the mass plus the internal energy at state 2. So this heat addition was given to us in the problem as 1400 kilojoules per kilogram, and then U2 was calculated from the specific volume ratio at 2. And so you can get your internal energy at 3 and calculate your temperature and pressure ratio. And the specific volume doesn't change. That was discussed in the problem. The volume doesn't change. So your pressure at 3 can be calculated using ideal gas laws. And it's a ratio of temperatures that's going to give you your pressure at 3. So state 4 will be defined by the pressure ratio at 4. Okay, so the first thing it asked us for was the temperature entropy diagram. I showed you that. Next thing it asked us for is the work of the cycle. So we know that the work of a cycle is the heat addition minus heat rejection. Heat addition was given to us. It was 1400 kilojoules per kilogram. And now the heat rejection, Q4 to 1, is going to be equal to H4 minus H1. And after your calculations, it'll come out to 855.1 kilojoules per kilogram. It's your work of your cycle. Your thermal efficiency is just equal to the work of the cycle over the heat addition, which is going to be 855.1 divided by 1400, and that gives you 61.1% efficiency. And our mean effective pressure is going to be equal to the work of the cycle over the mass divided by specific volume at 1 times 1 minus the inverse of our compression ratio. And here's my work. That's the last of the problem.